So I thank the organizer for inviting me to give a talk at this Women in Quantum Summit. So it has been an honor. So my name is Wenlin Tan. I just got my PhD recently, and now I'm joining IonQ as a senior physicist. So today I'll be talking about my journey in quantum computing simulation with trapped ions. So before I begin, I like to show this picture. So aside being a physicist, I'm also an artist. So I did this 3-panel comic. So as an atomic physicist, I shine lasers to the ions to manipulate the quantum operation. So in other words, I feel very awesome when I shine laser to the ions because it makes me feel like I'm a Jedi master. So, however, whenever I try to talk about my work in the public, the usage of the word atomic kind of trigger bad memories about the atomic bomb, but in reality, it's not. So it's just like me shining laser to atoms. And the last panel is me one of my aspect of my work. So I just manipulate laser light and shine it to the atom. And this is an exaggerated job part of my exaggerated part of my job. So for example, this is could have been a bad lab day. Yeah, I could spend hours and hours trying to align the lasers to the ion, and in the end, I could not align it. I feel like the ion is mocking me, saying that, "Haha, you miss again." So this is just a comedy comic strip that I did back in grad school. So next, I'm going to talk about a really just an in-depth introduction about myself. So I'm from Malaysia, coming from a small town named Mentakap. It's about 2 hours from the capital named Kuala Lumpur. So after I got finished my high school, and then I just realized that I need to apply for colleges, and I got accepted to University of Washington, Seattle, and I did my bachelor's of science in physics and applied math. So after I'm done with this degree, I proceeded to grad school, so which I ended up at College Park in University of Maryland to do my PhD physics, and finally now I'm at IonQ as a senior physicist. So a brief more story about me is as a kid, I like science. I enjoy science. I like to think logically. However, it wasn't easy for me to do science because I'm a girl. I got messages saying that girls are bad in science and math growing up. So this whole messages just make me literally doubt my ability to do science. But hearing all those were not encouraging at all. I also didn't have a mentor to look up to, and I didn't know where to ask for validation. So throughout the journey, it was I have a lot of time. I wanted to give up. I just okay, I should just go for something else, not science. But in the end, I just realized that I like science, and then I want to give it a shot, and I study more about science, and I really like it. So another point that helped me to verify that I really like science is there's a couple of examples. So I want to show one example. So I'm from a middle class family, and then I didn't have access to the best cable television back then, and I couldn't watch a lot of TV shows. So whenever I go to my cousin's place, instead of watching cartoons, I watch Mythbuster, Discovery Channel, Animal Planets. All those pointed that I like science. So with this idea, I decided to pursue science. And then when college application come by, I just realized that I want to study overseas. So one of the first motivation is I want to gain cultural exposure. I want to see the other world, what is happening in the other world. I chose the United States for its science and technology. I applied to some schools, but I was only accepted by University of Washington, or what I call UW. And I say I was very lucky. And then it wasn't easy for me to prep for the SAT because I only have limited amount of time, and the examination style is not something that I was used to. So throughout the whole process, I was lucky. And I would say that my acceptance to UW really opened up to tremendous opportunities. One of the example is I got to know like my undergrad advisor, Boris Bilinov, where he has a trap ion quantum computing lab. He gave me a lot of opportunity. For example, as an undergrad, I was in charge in like handling a real ion trap, which I found that this is a rare opportunity for an undergrad to do that. So I'm very grateful for the opportunity that he gave me. To now, I still stay in contact with him because he gave me a lot of advice. We always like interact like through emails. Like whenever I drop by to Seattle, I would just like give him a visit. So he is a mentor that I really cherish. So after my undergrad degree ended, I went to grad school, and Boris just like gave me a lot of recommendations that which school to apply, and finally I got accepted by University of Maryland. And of course, the saddest part is I need to leave Seattle, which I love a lot. So my next stage is College Park, University of Maryland, to pursue my PhD. And I also feel very fortunate that I got accepted to this grad school because this is one of the best atomic physics university, and is affiliated with Joint Quantum Institute. This means that I get a lot of opportunity to meet one of the best people in the field. So one of them is Chris Monroe. So I joined his trap ion lab, and in his lab there's a lot of trap ion aspect which I learned a lot. So throughout this 4.5 years of grad school, my experience that I gained there was very valuable to me. So after grad school, and then I realized that I enjoy College Park, and then I like IonQ, so I joined IonQ as a senior physicist. So this is only a brief story about me, but I would say that my journey to go there is not easy. At the start, I did doubt my ability to do science because all the messages that was conveyed to all the like social norms that I was pushed into as a child. My journey was indeed not easy. It can be as complicated as this image, like this, like a lot of direction. However, I still stay in science. Throughout the journey, I've met a lot of amazing people, co-worker. Let me proceed. I was saying that I feel grateful about all those opportunities. I feel that my acceptance to UW opened doors to me. But in the end, if I were not accepted to UW, I may or may not end up in quantum. But in the end, I will definitely choose science. Therefore, I urge people to seek ways for your dream. If you want to pursue quantum or science, just go for it. I cannot guarantee the path will be easy, but if you really, really enjoy it, it will be definitely fruitful. So please always ask questions. The person that you ask might not have the answer, but their friends or connection might have. So the thing I would like to convey is this is the strength of building connections. So that's the intro of the talk, and I apologize for the technical difficulties. Okay. So the main subject of this talk will be focusing about quantum computing and simulation. Because I'm an ion trapper, I will be talking mostly about the trap ion platform. So the idea of quantum computing and simulation was like allured by Richard Feynman. Even was like in 1959 during his APS conference, he was saying that when the devices are very, very small, it needs to abide to the law of physics. So at some point, we need to find new technology that that follows the law of quantum mechanics. And then following after in less than 30 years, he just like published a paper called Simulating Physics with Computer. In this paper, he was saying that can physics be simulated by a universal computer? And he proceeds saying that if in order to really understand quantum mechanics, we need a quantum computer or simulator. So this happened like about 40 years ago, or 30 years ago, which is like a long time, long time. But however, after 30 years, like right now, I would say that we are in the area of quantum computing and simulation. So you can see that there's a lot of platform uh, involved to study quantum computing, and I say this is an amazing opportunity for us. And plus, nowadays we have immersion of like companies to do the quantum technology. Therefore, I would say that this is extremely an exciting area to be in. And I thank the audience for joining this event. So next, I would like to talk about more about the TrapIon platform. So this will be just a summary. It will give like a flavor about how a TrapIon works. So in the TrapIon community, we in this field we use IF-Trap to confine ions with electric fields. According to Maxwell equation and Earnshaw theorem, which is depicted in this equation, a point charge cannot be maintained in a stable stationary equilibrium with static electric field. This is illustrated in this diagram. So I call this diagram as like a saddle, or maybe like a potato chip shape, where the confinement is along the x direction but not the y direction. So this means that ions can fall along the y direction, and thus the ions won't be confined. So instead we apply a time varying electric field. So you can imagine that this Pringles potato chip rotating, and this will yield a bowl. That's how the ions are trapped. Next, I'm going to show a simplified picture of the ion trap. So you can see that they are just like these circles are metal rods, and two of them are grounded, and another two of them are connected to a like time varying electric field. So by doing this, it will yield the confinement for the ion trap. Next, I'm going to show this is an example of the IF trap that I use during my PhD. So this is a macroscopic linear Blake trap where we confine the ion at the center. So you can see when this like magnified, you can see like there's a row of ions, and each ions represents 1 qubit. So the ions that I display here is ytterbium 171. So at IonQ and my PhD career, we use ytterbium 171 because it's a clock state qubit. When I say a clock state qubit, is another term to say like a hyperfine qubit. So the benefit of using a hyperfine qubit is insensitive to magnetic field noise by first order. So it allows us to have a longer T2 time easily. So this is just a brief atomic structure of the ytterbium, but I would like to point out two major aspects of the atomic structure where we encode the qubit in this 2s1/2 this state by 1,0, and the spin down in 0,0 state. So this is a crash course of TrapIon's platform. Next, I would like to just like talk about the differences between quantum computing and simulation, because I always get this question a lot when I try to explain to people about quantum computing. So what in reality, what's the difference? Both of them are similar, but at the same different. So this is this is what I think about both of them. So if you have a universal quantum computer, it can replace an analog quantum simulator. However, in the current quantum platform that we have in the world, there is no universal quantum computer yet. Therefore, I can see that the two major efforts in this field. One is to build a reliable quantum computer to perform quantum operation with high fidelity. Second, which is with the focus of analog quantum simulator, it does take a compromise of fidelity to pursue science. For example, in a quantum simulator, depending on the experiment and the observable measure, it does not require as high fidelity requirement as the universal quantum computer. Therefore, in order to build a quantum computer at the same time pursue interesting physics, both effort are required and they are happening in parallel. So all of them, they are just equally important. And also another thing about analog quantum simulator nowadays can serve as a test bed to a toy quantum algorithm, to pursue many body physics. So for now, this is what we have. And there are a lot of researchers or companies are trying to build a reliable universal quantum computer nowadays. So jump forward, that's about quantum computing and simulation difference. Throughout my PhD, I did quantum simulation. So the Travion platform itself can produce an effective Hamiltonian of the long-range transverse field Ising model, which I did during my PhD. And one of the projects that I led is produce a paper that is talks about domain wall confinement and dynamics in a quantum simulator. So I'm going to talk more about it in detail. So the whole idea about this experiment is about to investigate confinement of quasi-particle excitation with the long-range transverse field Ising model. The concept of confinement is very prominent in quantum chromodynamics in the presence of confining potential that increases with particle separation. You can see quarks and anti-quarks are bounded into hadronic particles. The hadronic particles is this gray circle. Although this quantum simulation experiment does not exactly describe QCD, it does give insight to the confinement effect. So therefore, this is an example of the usage of analog quantum simulator, which is very useful to pursue science. And so this is a gist of my experiment. So the first question asks how does the QCD confinement link to the Ising model? Komos show that a similar confinement effect can exist in the Ising spin chain, where domain walls quasi-particle are confined into meson-like bound state. Okay, there's a lot of information. Let me take a step back to explain this figure. This is a time evolution of the spin dynamics of individual particles. So the first thing that we need to answer is what's a domain wall? A domain wall is the boundary between two anti-aligned spins, like here and here. So which is this? So one type of configuration can represent as quark, another configuration represent anti-quark. So in the presence of a confining potential that increases with separation, the two domain walls will be bound, and this is analogous to a meson. So you can see that the domain walls in this figure, you can see that this domain walls is trapped and confined in the presence of a confinement Hamiltonian. However, with the absence of the confinement Hamiltonian, the domain wall will propagate like this dashed lines. So this is one of the ideas behind confinement of domain walls quasi-particle. Next, I'm going to this is going to be fast, but I want to show idea of the data that we can take using an analog quantum simulator. So this is a data. So when we look at the effect of confinement in thermalization, we initialize the spin in the top configuration like this and this and this. This plot are the individual spin magnetization measured along their initialization axis, which is this. And you can see this purple line is the calculation of thermal expectation value with respect to the initial state. When the initial state consists low energy eigenvalue of the confinement Hamiltonian like this too, the state is not thermalized as the spin state close. The spin state stay close to the initial state, so you can see that. So this is one of the effects of confinement. However, when the state is initialized far away from the low energy region of the many-body spectrum in the confinement Hamiltonian, the spin state thermalized to the purple line. So this is, here I'm just showing that what we can do with the analog quantum simulator. And for extra, and this is a sample image that I use in the paper where there's a 38 ion image. So where the blues are the ion represent as ion. So this is the end. So it can be fast, but I just want to give the audience a flavor about quantum simulation. And in this career, I'm very fortunate for the opportunity because I met like a lot of um, amazing people, and this whole project requires a team effort. So, in this pursuit of quantum simulation is a very strong collaboration between the theorists and the experimentalists. So, special thanks to my theory collaborator Alexei Osfu, Pangli Liu, Rex, and Seth for this like provides tremendous theoretical support, and of course my amazing teammates and also Chris for the help and resources for the result here. So this is a flavor for my PhD journey. And next I'm going to talk about my IonQ journey. So as Dennis has talked, like before we begin this presentation, I just defended my thesis around March, and I just like joined IonQ like 2 months ago. So I'm very new. I still have a lot to learn. And till now, I'm still having a lot of fun as I'm working in the R&D division to improve and develop better quantum technology. But but I cannot delve into details about that. However, I would like to just like talk about the IonQ Research Credit Program, which offers up to 10,000 free credits for time on the IonQ quantum computer. So IonQ is a quantum technology company with the goal to build and provide the best quantum computer for everyone. Therefore, I urge people to apply for this research credit program. This gives researchers the opportunity to test ideas ranging from all types of topics like quantum technology, quantum algorithm, and physics. By testing these ideas, your amazing ideas, with a quantum computer, it can lead to amazing discovery and even accelerate science. So personally, if I were a grad student or postdoc, there is not an experimental ion trapper, I would definitely apply and play around with it to test my ideas. So therefore, I strongly recommend the audience to try it. So that's the research credit part of IonQ. So another is like IonQ aspect. IonQ is like we do because we have like doing science, and then we also do like some publications. So this is a few example of publication. The first is like trying to optimize the quantum gates for a trapped ion quantum computer, and also we also have some articles about like for example, this like ground state energy estimation of water molecule on the trapped ion quantum computer. So this is the end of my IonQ talk and or general talk. But as an outlook, I would say that we are now living in a very exciting area of quantum computing. So if you're asking that if you should go to academia or industry, my honest opinion will say both ways have their pros and cons, but both of them share a similar similarity, which is either way you can learn and grow a lot. Therefore, I encourage anyone who are interested to do quantum, join and be involved in the quantum development. So I see that we still have like a couple more, there's like about 20 minutes. But if we cannot go through your questions, you can just like email me to this email, and then you can add me on LinkedIn. So you can ask me anything like career-wise, like going to grad school or industry, or maybe about science. So with that, I end my talk. Thank you.